Today
Okay.
we're doing an experiment with potassium chlorate and a gummy bear. And this will react with the sucrose and the gummy bear, making it oxidize, and it'll have some flame. So here we go. We're going to heat this thing up, and the potassium chlorate is going to turn to a liquid. When you first start heating it, make sure you keep the torch far enough away. We already cracked one of these things by sticking the heat right up against it right away and let it warm up a bit, and then you can move closer.
We just want you to notice the cool glasses they're wearing.
Always wear eye protective gear. You never know when something's going to explode.
That's right.
Alright, it's starting to melt here. Are you videoing?
Mm-hmm.
It's now melted, and when you put the gummy bear in, be sure to use a tongs because the reaction is instantaneous and it will burn you. Alright, there we go. And the lights are off so we can see the flame better.
Notice the fume hood.
Stuff reeks. Oh yeah.
2 clear solutions. Watch as we mix them together. Turns black. Okay, this reaction is called the starch iodine clock reaction. What is happening is basically if you have that there, starch and iodine react. Starch is an indicator of iodine. So when we put straight iodine in starch, it turns black. So what happened in this reaction, there's basically 3 things that are happening. The first step, I'll just be honest, I don't know everything about exactly how everything works, but in the first reaction, some products are produced that come into play in the second reaction, and they produce, and then there's this third reaction which makes blue colored complex. The important thing is the iodine. The first reaction doesn't have it. It comes, iodine shows up here, it's here in the second reaction, and then finally in the third reaction it messes with starch. It combines with starch to get a blue colored complex. So during these 3 reactions, what's happening is it's actually rate limiting. You pour in the one solution into the other solution, and those reactions are going on. Finally, after a little bit, the third reaction kicks in and it turns color. So if you kind of get it waits a couple seconds before it actually turns. So what we decided to do, the cool thing about this actually is you can dilute the starch solution with water and then pour it in, and it will slow down how long it takes before it turns black or blue. So what we did is we have 5 different solutions, each with different concentrations, starch solution, and as we pour in each of the solution that produces the black color, they're at different rates, so they all should go at different different speeds. So, as our grand finale, Derek will pour in different. So there's the starch iodine clock reaction.
Let's give him a hand. What's actually going on here?
All right, so basically we're demonstrating the reactivity of aluminum. And so what we have here is in that first one, we have some sodium hydroxide, and it's some pretty potent stuff. Basically, a little about aluminum is that its tinfoil is protected by a molecule-thin layer of its own oxide to protect it from chemical reactions with metal. But we like chemical reactions, so we want to remove that. And that is what the sodium hydroxide does. It eats up that aluminum, dissolves that top oxide layer so it can react with a metal. Okay, and then, so that's what the sodium hydroxide does. We put about 40 grams in about 200 milliliters of water right there in that far beaker over there. And so as you can see, here's this aluminum oxide. And what it does, if we would take it out, what it does is you just keep it in there, it dissolves the aluminum. And but if we would take it out, we'd have just, hopefully, our goal is just to have plus aluminum over on that side of the equation. We'd get rid of that oxygen. And here's the second equation. Here's our aluminum. And we add it to the sodium hydroxide and water. And what we should get is a hydrogen gas. That's just another equation basically explaining the same thing, what it does when we dissolve it. Now, this is a mercury chloride solution. What this does, it forms an amalgam with the tinfoil. And what an amalgam is simply an alloy mercury forms with metals. And the cool thing about these amalgams is that they can react with air. And so we want to remove the oxide layer so that we have elemental aluminum, and then put it in the mercury so that the mercury creates an amalgam. And then we, after we're done, just for the fun of it, what's supposed to happen, you stick it back in sodium hydroxide, and it just dissolves completely. So I'm just going to give it back to Brendan, and we're going to, what happened that last time is that we didn't stick it in the sodium hydroxide long enough. And so it didn't eat up all the oxides off the aluminum foil. So we're going to try it again. We're going to stick it in there longer, and we're going to see what happens. I'm just going to make this a little bit smaller.
Okay, so we'll just go through the demonstration again. See if it reacts the way it's supposed to.
Stick it in there longer.
Stick it in the middle. Now rinse it again. Like I said, that stuff is pretty tough. Now we might let it in here in this mercury a little longer too. You don't really want to mix the two solutions together.
Yeah, just get rid of that. Okay.
You're good.
As you can see, it's already taken that aluminum off there. And we'll wait now to see if this starts to warm up. That's what it's supposed to do, warm up and actually take the water droplets off of that, and the rest of take the water off of that. I
Oh,
don't know
yeah.
if you guys can see that back there, but it's starting to steam. Sodium hydroxide. Let's see if it will dissolve. It's not doing it. Still. Yeah, it stinks.
All right, go ahead. You guys ready?
And ready?
Mm-hmm.
Hello, today we're going to be doing a reaction with powdered sugar and sulfuric acid. It's going to create a carbon mound. So we have 100 milliliters of our powdered sugar here to 10 milliliters of sulfuric acid. And basically the powdered sugar is sucrose, which is made up of carbon, hydrogen, and oxygen. And in this reaction, the hydrogen and the oxygen comes off in steam, and we're left with just mostly carbon. Let's see exactly how much carbon it produces. Carbon is a very, very versatile element. It's also very abundant, about probably the 6th most abundant element in the universe. And yeah, because of its 4 valence electrons, it bonds with many, many elements. And there's more than 6.5 million known carbon compounds, different things that it's bonded with.
Now, are you sure you have enough sulfuric acid in there?
It's amazing how much carbon is actually found in the powdered sugar. I don't realize how much carbon there is in everything.
Think it's done growing? Pure carbon. That's what that is.
Hello, I'm Heidi. And I'm Emma Byler. We will be doing the jumping sodium experiment. And we have all of our ingredients here. We have water, phenolphthalein, and paint thinner, and sodium. We will start with water into the test tube. Put about an inch. And the phenolphthalein, we'll put 3 drops, which this acts as a pH indicator. 1, 2, 3. And then the paint thinner will go on top, and it should just sit right on top of the water, and you should be able to see the difference in between the two. It's sitting right on top there. You put like basically the same amount as water on top. And now we've got sodium. And it's jumping. As you can see, it just stays in the paint thinner. Basically what's happening is as the sodium hits the water separates into hydrogen gas and hydroxide, which is what we're doing up here. And you get the sodium hydroxide and hydrogen gas. And since it's an exothermic reaction, the hydrogen gas expands, and that's what is also causing the sodium to keep bouncing around in the paint thinner and keeps it from going on down in the water. And also the sodium hydroxide is an alkali, which is causing the water's pH to be changed, and your pH indicator is pink. The experiment was called for gas, but we used 2 different kinds of gas, and it did not work. So we substituted paint thinner, and it was having issues sticking to the side, which we think it was from the paint thinner, but right now it's working pretty good.
That's awesome that it turned out.
Now, could you guys tell us, would it be safe to just drop that piece of sodium into water alone?
Oh yeah.
And now for our intermission show, we're going to have a little bit of fire eating.
Alright, my name is Marcus King.
And I'm Christopher Nosley.
Today we're doing electroplating. Well, if you want to get technical, it's electrodeposition, where we have a quarter and some copper, and we're going to try to put some copper on the quarter. The way this works is you have you use electrolysis. You have a circuit here with positive going in here and negative going in here. Your anode is the copper, cathode is the quarter. You put them in a solution, salt solution, copper salt solution, and basically it ionizes, and the ions go across and plate onto the quarter. You can see the molecular formulas here. We don't have a really specific equation for how things work. But that's how
What we're doing now is mixing the copper sulfate solution. And so we put 1 clip of this.
This is sulfur or gases. And this is copper sulfate. There's 100 milliliters of warm water in there. If the water is warm, it will plate better, supposedly. use alligator clips to, you have to have a DC converter, we use DC current, and use alligator clips to hook those up.
As you can see, this quarter right here is a regular United States quarter. There's nothing, it's just a normal quarter. Show it to you once we're done and show you the difference.
And we clean this, first of all, with steel wool and then with soap and water. Because the cleaner the surface to get plated is, the better it plates. We've sort of had mixed success with this. Sometimes it works and sometimes it doesn't. So you use copper wire to hang this in the beaker. And we have a piece of copper from just a regular copper pipe. You hook up the negative end to the quarter, the positive end to the copper. If I can get this connected here. Hold that up. And then plug it in. And there it goes. You pull it out right away. Got it.
I'm going to do this.
All right, can you pull it out just one more time so I can get a better look at it? Let's take a look at it once. Wowzers. Got copper all over it already.
We're going to plug it in.
You have to make sure your electrodes aren't touching in there.
What is that?
I never tried it.
Just lift it out a little wee bit. Too high. Just barely hold it above the water.
Like
Yeah. Wow.
that. As soon as you drop it down, it just starts bubbling away again. Try cleaning that thing out.
Where are you facing it?
Just let me try. I'm going to try something like this. I'm going to die.
For the record, no quarters were permanently defaced in the making of this video.
Hi, I'm Jordan Lehman.
And I'm Justin Graybill.
We actually ran into this experiment that we're going to do for you today by a bit of an accident. Well, notice we're outside. That's so we don't set off any smoke alarms or in a worst case scenario maybe burn down a building or something like that. You also notice that we don't have the help of a blackboard, so we're just going to explain to you what we're doing. So what we have here is potassium chlorate and sugar. And we're going to mix them up and mix them well and then put them on this burner. So Justin,
100 grams of potassium chlorate and 150 grams of sugar. So 2 to 3. Just mix them up in this tin can. They shouldn't start reacting until we put them on the heat.
You guys might want to get that potassium chlorate bag away from there before you do anything.
We already have this burner pretty hot. I can feel quite a bit of heat coming off it right here, so that will make the reaction just go more quickly if you do that.
Shake it up good so it's mixed well. Set it on there. Step back.
Victoria's gonna be right behind the smoke.
You can really scare somebody with a smoke bomb. Oh my goodness.
We should do it tonight.
It's the residue.
Loaded.
Yeah.
After volleyball when it's dark.
I'm Valerie. And I'm Sierra. What we did is we tried to grow some crystals. And so I'm just going to tell you how you grow a crystal. What actually happens when you grow a crystal is that you separate the molecules into individual groups, kind of. Like, anyways, and so when you let the water evaporate, what happens is the molecules fall together in their natural crystal form. And yeah, it's pretty easy and pretty cool. So, yeah, we have copper sulfate here and sodium nitrate, the 2 crystals that grew. And then we're trying to grow some rock candy over here, which is basically sugar water. And it's kind of coming along, but yeah.
The ratio in this sugar water is 3 cups of sugar to 1 cup of water, which is a ton of sugar.
Yeah. So we just, we heated our solution up really hot until it was super saturated and we couldn't dissolve anymore, and then just set it aside somewhere where it wouldn't be disturbed and let the crystals grow. I'm going to talk about this one. You'll get to see it soon, but it turned out really, really nice for us. And this one is copper sulfate, and it's like a pentahydrate compound. This particular compound can form several different types of crystals, and it's all due to its hydration. So the blue color that you see is actually the water molecules in there, and what would happen if we would dehydrate this crystal, it would actually change colors. So that's what that 5H2 is about. And yeah, I guess now if you want to come look at it.
Actually, you could actually almost, like, I mean, we're not going to be able to finish growing it. If somebody wanted to try it, they could. Hold me back.